Hello, everyone. Can you hear me? Okay, great, great. Yeah, thank you, everyone, for coming. Let's wait another minute, and then we'll start um, the lecture. Okay. Okay, let's start the lecture. You see that we have quite the crowd here. That's great. I'm very happy to see that. So yeah, let's start. So good morning, everyone, and welcome to our webinar on understanding the receiver operating characteristic, or ROC curve. My name is Nir Regev, and I'm the founder of AlephZero.ai. It's a company specializing in advanced signal processing and AI solutions for various applications. Before we dive into the fascinating world of ROC curves and dive into example that I prepared for this lecture, I'd like to take a moment to express my gratitude for your presence here. This is quite a turnout here, and it's really great to see you all here. Today's lecture goal, at least from my standpoint, is to give you guys the tools to live here with a solid understanding of the ROC curves, their constructions, how do you construct it, how do you use it, how do you make decisions with it, and its crucial role in evaluating the performance of binary classification models. Throughout this webinar, we'll explore the fundamentals of ROC curves, including what we call PD in radar, the probability of detection or true positive, false positives, what we call PFA, and how these metrics provide invaluable insights into the effectiveness of our classification and detection models. We'll also delve into the significance of the area under the ROC curve, what we call, in short, the area under the curve, or AUC, and learn how to interpret various shapes of the ROC curves to gain a deeper understanding of the model performance. We won't stop there. We will go beyond the theoretical concept and discuss practical applications of the ROC curve across different applications, data science, and obviously, because I'm from the radar world, we'll also dive into some radar examples. And you'll discover how these powerful tools influence real-world decision-making processes and how you can leverage them to prioritize your own models. As we progress through the session, we encourage you to actively participate, ask questions, and share your own experiences. We have a fantastic group of attendees here. It's really quite a turnout, and I really believe that the collective knowledge and insights we share will further enrich our learning. So by all means, just ask questions if you want in the Q&A section. Once again, welcome to the webinar, and thank you for being here. Let's dive into the world of the ROC curve. Let me share my screen. I'm actually sharing my screen. Can you see the presentation? Give me a thumb up if you can. If this thumb up here. Yeah, great, great, perfect. Okay, so as you can see, this is the first slide. I already did the introduction. These are the websites. This is my company's website, and this is my personal website in which I publish scientific stuff like this, for example, but also career development, engineering career development, and other stuff. You can check it out if you want. Okay, so what is the ROC curve? The ROC curve is standing for receiver operating characteristic, is a graphical representation of a binary classification model's performance. What is a binary classification model? Let's think about the way I teach that in detection theory course is think about a smoke detector, okay, like we have in our houses. And this smoke detector is either has, most of the time, the not or the null hypothesis is no smoke present. And the alternative hypothesis, H sub 1, is there is smoke, sound the alarm. So this is the classical example for a binary classification, or binary detection, or binary decision making. Okay, these are all synonyms, and these kind of frameworks, for example, the smoke detector, it suffers from two errors. One is when there is no smoke and we sound the alarm. Okay, this is what we call a false positive or false alarm. This is why we call it false alarm in radar, because we sound the alarm when there is nothing. There is nothing, but we think there is, or the detector thinks there is. The other error that we suffer from is the what we call the misdetection, when there is a fire or smoke and we don't report it, we don't sound the alarm, right? So these are the two types of error that we see in binary classification and throughout classification theory. And these errors are connected to each other by the way of the ROC curve. And we will see that these errors are increasing and decreasing together. Okay. So the ROC curve is an essential tools for evaluating and comparing binary classification model. Now, how do we do that? For example, in the case of a smoke alarm, we have mainly, let's say that this is time and this is energy of the signal. And mainly we have some noise running. Most of the time there is no smoke, there is no fire. And suddenly the detector spikes with a peak because there is a fire, okay? And the peak can have a duration in time, on the time of the fire, and then we will sound the alarm if this level of energy, for example, is greater than a threshold gamma. Okay, so this is how we build or are we building classification models or detectors. And it doesn't matter if it's machine learning algorithm or it's this kind of energy detection thresholding. The concept is the same. We seek a threshold and we report what we think to be a true positive if it passes the threshold and none otherwise. Let me check the question and answers section. Let's see if we have something there. Okay. If you have questions, please type it in the Q&A section, not the chat. Okay, so I will just take a look at one section. Okay, next. Okay, some history of the ROC curve. The ROC curve in 1941 in World War II, the ROC curve were invented by electrical engineers. Why? For detecting the enemy objects in battlefields, which leads to its name, receiver operating characteristics, because the radars had receivers, and that's why they call it like that. Nowadays, the ROC curve was borrowed from then to be available for machine learning, data science, and medical device, and so on and so forth. In the 1960s, it actually was entering signal detection theory as a subject. And psychology in the 1970s, it was introduced to the medical field for diagnostic testing. And since the 1980s, it's widely used in computer science, electrical engineering, classical machine learning, and even deep learning. Okay, let's discuss some properties of the ROC curve. First, the ROC curve is a two-dimensional curve. Okay, it has two axes. The horizontal axis is the false positive rate, or P, what we call in radar P false alarm. Okay, the vertical axis is the true positive rate, or what we call in radar PD, which is probability of detection. And the ROC curve is this line here, and this line is PD versus PFA, or true positive versus false positive. That's the ROC curve. That's the definition of a ROC curve, and that's how we build it. How do we actually build the ROC curve? Let's go back. You see this? So what happens if I set the threshold very, 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 very low? If I set the threshold very, very, very low, even lower than that, I can get more false alarm, right? Because I threshold also noise will pass the threshold. Noise level will pass the threshold, and then I will get more false alarm. Okay, if I take the threshold to 0, I will get a false alarm rate of 100% and a detection rate of 100% also. Okay, now what happens if I take the threshold and I move it up? As I move it up and more and more and more and increase it, I will set the threshold above the maximum level of the peak, and I will detect nothing. So there will be no false alarms, but there will also be no detections. Okay, so the threshold is what governs the variability of this curve here. Okay, so as we progress through PD PFA pairs, or true positive false positive pairs, and we plot it, we change the threshold in order to do that. Okay, now what is this straight line y equals x? This is what we call a random classifier, which means it's a classifier that is flipping a coin and deciding like that, so to speak. And every ROC curve in nature is always above this line. Okay, so if you do some machine learning exercise in your works or in your research, and you get a ROC curve that looks like this, you got the axis inverted. It cannot look like this. The ROC curve has to be above this line, and it also has to be concave. We can prove that, but not in this lecture. Okay, so the ROC curve is concave, and it's above this y equals x line, or PD equals PFA line. Let me go and check the questions. No questions. Okay, let's continue. Okay, we discussed how we build the ROC curve, like with threshold. We change the threshold from what will be the threshold in this point. The threshold, let's call it gamma, in this point is infinity. Why? Because we detect nothing. We increase the threshold so much, nothing is detected, and nothing is reported as false alarm. Okay. Now we decrease the threshold. We decrease the threshold until here the threshold gamma will be 0. Okay. When the threshold is 0, everything passes the threshold, and everything we see, we report. It's 100% false alarm and 100% detection rate. So the points, this point and this point right here, are part of the ROC curve. Okay, usually in radar at least, but this can change depending on the classifier. But if we are taking a classifier likelihood ratio of x that is equal to the PDF under the first hypothesis divided by the PDF under the null hypothesis, we get that this slope here, this slope, or the derivative of the ROC curve, is the threshold gamma. This is true for what we call the likelihood ratio test, like I written here, but it's a function of the slope. The slope is a function of gamma always. Okay, so as gamma is changing from infinity to 0, the slope will change as well, from something very large to 0. Okay, and as we said before, the points 0, 0, and 1, 1 are a part of the ROC curve. The ideal point in which an ideal classifier will be is this point, in which we have 0 false alarm and 1 probability of detection. Okay? This is this, and then the curve will be a straight line up and a straight line to the right. Okay? That will be the curve for the ideal, unless the classes that we want to discriminate or classify are completely far from each other, which is not the case really. Usually in real life, we won't get this kind of ideal. Usually we will get a concave shape like this, and we will have to choose our operating point on this curve. And what does it mean to choose this point? It means to set a gamma, a threshold to be, let's say, gamma naught. Okay, and the optimal point, for example, in this case that we chose, is the PFA is 0.1 and the PD is 0.69. Okay, so that will be the performance of this classifier if we set gamma to be gamma naught. The area under the curve, as I drew here, this is the area under the curve, all this section. And this is a metric or a proxy for the performance of the classifier as a whole, or the detector. Okay? It's a scalar. The maximum of the scalar is 1 because that's the whole square, 1 times 1. Okay? The minimum of this is this line, which is 1/2. So it's a scalar. It can range from 0 to 1 theoretically, but practically it cannot be less than this line. So it's between 1/2 and 1. And as we approach 1, we are better, and we approach 1/2, we are more random. Okay, so this is the area under the curve. And once we are, when we are benchmarking or comparing classifiers, we can compare this metric AUC, area under the curve, as a metrics for performance. So for example, if I have a classifier that performs with an AUC of 0.7 and another one with a 0.9, I will choose the one with the 0.9. I will because it has better ROC performance and it has better opportunities for me to get less PFA and maximize the PD. So for example, if this area under the curve here is 0.7, let's say this is 0.7, and I have another option that is like this, let's say 0.8. Obviously, if I choose this point as an operating point, I get better performance, less PD and more PD and less PFA, right? Less PFA because it's to the left of this, and more PD because it's greater than this red point. Let me check the questions. No. Okay, great. Okay, so the conclusion is the ROC curve and the AUC are valuable tools for evaluating binary classification. We understand the properties and how to interpret the ROC curve, and it's crucial for model assessment. And the ROC curve history, starting from World War II, and it's very, very vastly used these days as well. Okay, let's see a code. Let me stop sharing here and let me share the screen with the code. Second here. Before we go and dive into the first example, this is the first example. There will be another one, but before we dive, let's see if we have any questions. How would one choose between two equal AUCs, but when the slopes differ? Oh, that's a good question. So if okay, so theoretically, two equal AUCs has to be the same exact curve. Okay. Now the slope, if the slope differs, it will introduce another AUC. But sometimes we don't have enough points in our data or the resolution to actually plot a very smooth type of ROC curve. The ROC curve can, in practice, if we plot it, can be noisy as well. So when we assess the AUC, the area under the curve, we try to interpolate points there. Okay, so sometimes even different performance will get the same or very close to AUCs. So how do we pick the best? So that's another question. Maybe the one with less power, the one that costs less in area, the one that is easier to implement, and so on and so forth. I hope this answered the question here. Okay, let me share the screen again, and we'll dive into the code. Okay, so this example, this is actually an example from my website. So the people that are paying, they have a membership. It's $6.99 a month. They have access to many examples like this. So this is one of them, and the title is the generalized likelihood ratio test for iris species classification. So in this data set, we are investigating, trying to classify between different, I guess, sub families of flowers of the iris flower. Okay, specifically, we will start by trying to separate the Setosa species. Oh, sorry about that. Okay, so we're trying to separate the Setosa species. Wait, can you guys see my screen before I progress with this? Give me a thumb up if you can. Great, perfect. Okay, thank you, Alexandra. Let's continue with it. So we are trying to separate the Setosa from the other two species, namely the versicolor and the virginica. This is the first part of this demo or example. And in the second part, which will be more interesting, we'll try to separate between these two, okay, this versicolor and the virginica species. So we are going to use what we call a GRT, generalized likelihood ratio test. Okay, it's a powerful statistical hypothesis testing method or a classification method. It compares the likelihood of the two competing hypotheses based on the observed data. Okay, now here in this piece of code, what we do is we load the data set, we split it to train and test. I'm not going to go into why we do that. I assume that we know that already. But just in a few words, we would like to train on some portion of the data and then test it on the other portion that the classifier hasn't been trained on. Okay, and then we're going to take the training data set and estimate the kernel density using the Gaussian kernel. So specifically, we're going to estimate the shape of the probability density function or the density distribution function of the data for both classes. Okay, and let's run this. Okay, so while it's running, what we do, we load it, and as I said, we estimate the density by using a kernel estimation method. Now, this is using the sklearn, the scikit-learn package or library. Okay, what is the general likelihood ratio test? We define an hypothesis, two hypotheses. One, H naught, or the null hypothesis, is that X, the measurement or the feature vector, belongs to the setosa class. And the other, the alternative hypothesis, H sub 1, is that X belongs to the non-setosa class, versicolor or virginica. And we are comparing these two hypotheses or in a way that is the ratio between them. So we take a new measurement that we don't know which class it's belonging to, and we plug it in to the different probability density function, and we evaluate the ratio. If this ratio is large, there is essentially a higher likelihood of it belonging to H1. If it's not large, if it's very low, then a higher likelihood that it's belonging to H naught. And we compare this against threshold, gamma. Okay? And obviously, in practice, we can take the logarithm of it and comparing the difference of these log likelihood. So it's called the log likelihood ratio in this case. Let's run this. This is what we do here. And we see we did calculate the log likelihood ratios. You see, this is this line here. And then we set the threshold to 0. Now this threshold now, because it's in a log scale, it can go from -infinity to infinity, okay? Because we took the log of it, but we set it to the center, 0. And we see that we have an accuracy of 1. What does it mean? That we have a perfect separation between these classes, the non-setosa and the setosa classes, okay? The next section here is where we do a ROC curve and a threshold selection. Let's see how we do that. So we compute the ROC curve. We set a threshold TPR and FPR, false positive rate, true positive rate, and threshold as outputs of this function, ROC curve. This is also in scikit-learn metrics. And also it has the ROC AUC score. Okay, member, and we can basically calculate the FPR TPR for plotting and the threshold, and we can calculate the AUC. Okay, and now we just plot it. Okay, so we see what is usually doesn't happen, but I put it here just for the sake of this example. Okay, this data set is very minimal. Okay, we don't have a lot of data points, and that's why it looks like as if we can separate these species based on the feature vectors completely. But if we sample infinite amount of flowers, we probably have a few anomalies that will make us wrong, so to speak. But in this data set, we don't see it. So for this test data set, we get a perfect ROC curve. You see, this is the perfect ROC curve. The AUC is 1, and the ROC curve is spanning these two axes, the PD and the PFA. Okay, now this is what I call this is just an introduction to the concept of the ROC curve. We are further investigating it. We are doing the histogram to see why do we have such a good separation, and we see that the setosa class is somewhere here in -10, -15, and the non-setosa class is spread between plus, I don't know, it's 7 maybe to plus 65 or 70. And there is a gap between, there is a nice gap between them in which we can set the threshold to and get perfect classification. If we take the mean and variance, we can see that the mean is -11 for the setosa class and plus 28 for the non-setosa, so they're very far away from each other. And one has a large variance, one has a very narrow variance, very small variance. Okay, now let's get hairy, so to speak, and add a add another twist to this classification exercise. And now we're going to use the generalized likelihood ratio test, or the ratio between the likelihood function. But now I want to separate between versicolor, oh, sorry about that, between the versicolor and the virginica. Okay, these are the two non-setosa classes. Why? Because they overlap, and here we don't get a perfect type of classification. And we go through this exercise again. We estimate the kernel density, and this is, let's run this code. So we estimated the kernel densities using these Python and scikit-learn packages. And then we plot the GLRT, the generalized likelihood ratio test, and its distribution. Let's run this code. Here we do the log likelihood for the versicolor. We calculate the log likelihood for the virginica. We estimate the kernel density for each class. So now we have the density, and then we plot them. And here, suddenly, we see that these distributions are overlapping. Okay. Now, sometimes under certain requirements, let's say, if we want to change to select the threshold, we can select the threshold to be right here between these two PDFs. Okay, but most of the time, let's say 99% of the problems in reality, this kind of threshold setting is naive and wrong. Okay, and so how do we set the threshold in this case? Let's see. And this is the bonus. This is not specifically related to the ROC curve, but we see how it relates. Okay, so ROC curve and threshold selection. Let's first plot the ROC curve and the AUC. And here we see what I said before, is that the ROC curve here is like kind of like a step functions. It's not a nice smooth ROC curve. We don't have a lot of data. We don't have a lot of resolution here, but we can still estimate the AUC, which is 0.97. Okay, and we see that this ROC curve, this empirical ROC curve, is above this line, and it has this concave shape, this ideal concave shape, and so we know that we didn't do anything wrong, so to speak. Okay, now here, what I want to do now is I want to see, we see in the ROC curve that we can choose a alpha, the error alpha, also the PFA, to be 0.07, somewhere here. And this will bring us into somewhere around 0.7 in probability of detection. Okay, and we can calculate the threshold using the Neyman-Pearson's theorem. Now, this method is also a bonus for this lecture, and this method is the following. We have, let's go back to this graph. Okay, the PFA, the false alarm probability, is the area under the tail of this blue line. Okay, from where the area starting from where? Starting from the threshold. So let's say the threshold is right here. Then we take a line up to here, so it's -1, and we integrate the blue line from -1 up to infinity. Okay, and this area under the tail is the false alarm rate. We want this to be 0.07. Okay, let's say for the sake of the example, we want this to be 0.07. In other words, we are doing something that is called CFAR, a constant false alarm rate, in which we are forcing our classifier to operate at a certain PFA level, false alarm level, and in the same time maximizing the performance of the detector, or maximizing the detection probability. Okay, this is called the most powerful, or locally most powerful detector, and you can see it. What I described in words, you can see it here. The integral from gamma up to infinity of the on the null PDF is this false alarm rate, which we set to be 0.07, okay, right here. Okay, now we're not going to solve this integral on paper, obviously. We're going to solve it numerically with Python. And this piece of code, by the way, you're going to get this piece of code, okay? I'm going to share this notebook with you right after this lecture. So this piece of code is doing this calculation for us. And let's run it. And we can see here, it's also plotting it for us, that the threshold is actually not in this intersection point. It's to the left of it, the threshold that we picked. And we picked the threshold. In other words, we let Python solve this equation with respect to gamma, the threshold. Okay? And how to do that? We integrate, we do a one-dimensional integration on the Gaussian PDF and so on. So this is how we do that in Python. And we set the threshold to the threshold that we found. We let Python solve it for us. Okay, this is from the library SciPy optimize. We use the fsolve optimization method, and we solve for the threshold. And we solve this integral equation. We set the threshold to be whatever we got as a result. And here we can see now the line of the threshold on this graph. Okay, now we can use this threshold now to classify all the test data that we have, and to get a confusion matrix that gives us an accuracy of 0.93, okay, or 93% accurate, in which we have 16 versicolors classified as versicles and one that is not, and the same for Virginica, but this is 12 and 1. Okay, so we can see here that this classifier that we built with understanding the ROC curve and setting the threshold and the operating point on the ROC curve gave us an accuracy of 0.93. Okay, before I go, then I describe what I did with the code and so on and so forth, and I describe a conclusion. This is for you guys to refer to after the lecture. I want to stop sharing my screen now and see if there are questions about this. Okay, so no questions so far. Let's go back to the presentation. We have still a few more minutes for this session. Okay. I'm going to share my presentation again, and please give me a thumb up if you can see it. Nice. Thank you, Lucas. Thank you, Alexandra. Thank you, Michael. Okay, let's go back to the presentation. Okay, so we stopped here. Let's progress through the presentation. Okay, the next example is a radar example. Okay, this is the world that I'm coming from. So I'm simulating a radar, a FMCW radar here, with a carrier frequency around 77 gigahertz, 4 gigahertz bandwidth, a chirp duration of 50 microsecond, 2048 samples per chirp, and which basically result in a sampling frequency of about 244 megahertz. The detector that we are using is a constant false alarm rate detector, which we call in radar CFAR. Without going into how it works specifically, in radar, we are getting a peak and noise in a what we call the range axis. Range is the distance, okay? And we have to detect this peak. So we set a threshold and we run a sliding window with some guard and reference windows to the left and right of it to estimate the noise level and then compare it with the threshold. Okay, that's in a nutshell what is done here. So the guard beams is 2, the reference window is 20 beams, 20 beams to the side of the peak to each side of the peak that we are using for estimating the noise level. And the threshold range is between -15 to 15 dBs in 0.5 dB increments. And I am going through the motions of estimating the performance, or the AUC, the area under the curve, for the pipeline, which include different window functions before the FFT. So Henning, Blackman-Harris, Hamming, Gaussian, and Tukey with alpha of 0.7. A Tukey window is a window that is flat up and then it rolls down. And the 0.7 is what's the percentage of the flat with compared to the whole to one, basically. The maximum is one, which is a rectangular window. I think 0.8 is a Henning window, and 0.7 is between. Okay, let's go back. So the Monte Carlo simulation logical flow is the following. We start, one second, start analysis. That's the analysis. Okay, so we generate, where is it? Where is it starting? So here we start, we generate a pulse, we add noise, we apply a window function, we perform the FFT, we apply C for detection, we calculate probabilities and SNR, we increment the counter, and we check the counter. If the counter has reached 10,000, for example, we stop. Otherwise, we go ahead and we generate another pulse and so on, another chirp, and so on and so forth. Okay, and for each, we calculate probabilities for the ROC curve and AUC and the SNR, and the mean SNR, I would say. And the results analysis is plotting the ROC curve, calculate AUCs, generate AUC bar plots, calculate mean post FFT SNR, and generate an SNR bar plot. Okay, that's the simulation logical flow. And let's see the results. Okay, so we have the results here. Here, on this colorful diagram here, or plot, we can see the ROC curve for different windowing functions. Okay, so we can see here, and these are the AUCs, this bar plot here inside are the AUCs of each windowing. And we can see that the maximum, the most performing, window, okay, in terms of AUC, area under the curve, is the Blackman-Harris window for the data that we generated, okay, data plus noise. And then the next is the Gaussian window, and then the Henning window. And we can also see it here, the red curve here is taller than everyone else, so it has more AUC area, and it's the top performing, and this is the Blackman-Harris. And then very close to each other, we have the Gaussian and the circle, the Henning, and then the rest. Okay, and you can see the ROC curve and you can see the AUC. Now, let's see something that is very counterintuitive. Okay, in terms of the post-processing SNR, or the average post-processing SNR, the Blackman-Harris is not the best. Okay, so unlike common methods that we know in radar, SNR does not indicate, okay, it's a good indicator for a lot of things, but it's not the only indicator that is affecting our classifier performance, because we see here that in terms of the area under the curve, this classifier, the Blackman-Harris window, is the best. So even if we, in terms of the mean SNR, the post-processing mean SNR, we, I guess, penalize ourselves with maybe half a dB with comparing to this, or maybe 1 dB, we are still going to get in the average scheme of things, we're still going to get a better performance if we choose the Blackman-Harris window. Questions about this? Let me check the question and answers. Okay, there is a question here. What is Doppler ambiguity? Okay, Doppler ambiguity is where, I mean, it's not related for this, but to this specific ROC curve lecture, but Doppler ambiguity is aliasing in the frequency axis, in the Doppler axis. Okay, that's where you surpass your maximum Doppler, your maximum unambiguous Doppler, and you fall back into the available spectrum. What is the use of the Neyman-Pearson coefficient? Okay, the Neyman-Pearson coefficient is something else. Okay, it's not the Neyman-Pearson theorem that I showed you is not the same as the coefficient. And how could one choose between two equal AUCs? Okay, so this one I already answered. Any more questions, please type it in. And let's go back to the presentation. Okay, so some words about my company, Aleph Zero. This is what we do. We help our clients. By the way, it's nice to see some of our clients here in this lecture. We help them in their DSP and algorithm pipelines from sensors and signal processing, AI for computer vision, and data science and language models. That was a service that we introduced in the last year, I guess. Moreover, we design FPGAs and optimize neural networks on FPGAs and ASICs and quantization of neural networks. We're experts in that. And we do it for DSPs, GPUs, and FPGAs and ASIC. My personal website, check it out, drnirregev.com. I publish a lot of algorithm, machine learning, signal processing, AI content. I publish the upcoming lectures here, there in this. By the way, on this Friday, there is another lecture on linear regression, least squares estimator. And there are also some available courses. Now there is an available course that is launching in a month and a half that is titled AI in Radar and Applications. And it's a very comprehensive course about how to use AI in radar. More information, either email me to this email address or sign up for updates on these web links. Thank you very much, everyone, for attending this presentation. I hope it was helpful, and I hope I got to teach you some stuff that are new to you. There are also another question here. What is the cost of the AI in radar course? The cost is I think it's $1,300, but for early bird, which is still running, early bird registration is still running until the 25th of May. There is a 40% discount. If you want it, just reach out to me and I will give you the discount code, the 40% discount code. What else do we have here in terms of questions? Okay, nothing in terms of question. Let's see in the chat if I missed something. Okay, Saeed, thank you. I appreciate your comment here. And also Prem Kumar, thank you very much, guys. I appreciate you coming in and listening. And I really, I mean, if you can join the future lectures as well, that'll be great. And in any case, these lectures are recorded, and for the members of my website, they will be published. Thank you very much. Yes, I will. Yes, Alexandra, I will share the notebook, the Python notebook with you guys. Right after the lecture, you will receive an email from me. In this email, there will be a link to my website. In this page, there will be all the materials, including this presentation, including the notebook. And if you guys can spare a few minutes of your time to give me a feedback, there will be a Google form for you guys. It takes 2 minutes. And if you guys can do that, I will very much appreciate that, because in this, you can influence future topics of lectures, because I want to tailor the content to the society that I'm lecturing to. So yeah, thank you very much, guys. It was a pleasure having you here, and I hope you enjoyed it. Bye bye. Yeah, I can suggest a book on AI in radar. Actually, in AI in radar, there is not a lot of books on this topic. Let me check it out for you. Please email me with this request. Okay. Thank you.